So our topic for today is about threads. No? So the basic idea is that the several components in any complex system will perform particularly some functions that contribute to the overall functions. So after this lesson, you should be able to understand the distinction between process and thread, describe the basic design issues for threads, explain the difference between user-level threads and kernel-level threads, describe the thread management facilities in Windows, thread management facilities in Solaris and Linux. In this discussion, we examine some more advanced concepts related to process management, so which are found in a number of contemporary operating systems. We show that the concept of process is more complex and subtle than presented so far, and in fact embodies two separate and potential independent concepts. One relating to resource ownership and another relating to execution. And this distinction has led to the development in many operating systems of a construct known as a thread. So process and threads. So the concept of a process as embodying two characteristics. So we have the resource ownership, which is the process includes a virtual address space to hold the process image. The process image is the collection of program, data, stack, and attributes defined in the process control block. So from time to time, a process may be allocated control or ownership of resources such as a main memory, input-output channels, input-output devices, and files. So the operating system performs a protection functions to prevent unwanted interference between processes with respect to resources. Scheduling or execution. The execution of a process follows an execution path or the trace through one or more programs. And this execution may be interleaved with that of other processes. Thus, a process has an execution state like running and ready in others, and a dispatching priority, and it is the entity that is scheduled and dispatched by the operating system. Some thought should convince the reader that these two characteristics are independent and could be treated independently by the operating system. And this is done in a number of operating systems, particularly recently developed systems. So, to distinguish the two characteristics, the unit of dispatching is usually referred to as a thread or lightweight process, while the unit of resource ownership is usually referred to as a process or a task. Okay, so multithreading. Multithreading refers to the ability of an OS to support multiple concurrent paths or execution within a single process. The traditional approach of a single thread of execution per process, in which the concept of a thread is not recognized, is referred to as a single-threaded approach. The two arrangements shown in the left half of this figure are single-threaded approach. Then the MS-DOS is an example of an OS that supports a single user process and a single thread. Other operating systems, such as some variants of Unix, support multiple user processes, but only support one thread per process. The right half of this figure depicts multi-threaded approaches. So a Java runtime environment is an example of a system of one process with multiple threads. So of interest in this section is the use of multiple processes, each of which supports multiple threads. This approach is taken in Windows, Solaris, and many modern versions of Unix, among others. So we give a general description of multithreading. So the details of Windows, Solaris, and Linux approaches are as follows. In multi-thread environment, in multi-threaded environment, a process is defined as the unit of resource allocation and the unit of protection. And of course, they are associated with processes. So a virtual address is space that holds that process image and protected access to processor other processes, files, and input-output resources. Within a process, there may be one or more threads, each with the following: a thread execution state, a saved thread context when not running. One way to view a thread is an independent program counter operating within a process, an execution stack, some per threaded stated storage for local variables, access to the memory and resources of each process shared with all other. So in this figure, it illustrates the distinction between threads and processes from the point of view of process management. So in a single threaded process model, so there is no distinct concept of thread, for example. No, the representation of a process includes its process control block and user address space, as well as user and kernel stacks to manage the call or returns behavior of the execution of the process. While the process is running, it controls the processor registers. The contents of these registers are saved when the process is not running. In a multi-threaded environment, there is still a single process control block and user address space associated with the process. But now there are separate stacks for each thread, as well as a separate control block for each thread containing register values, priority, and other thread-related state informations. So, thus, all of the threads of a process share the state and resources of that process. They reside in the same address space and have access to the same data. When one thread alters an item of data in memory, other threads see the results if and when they access that item. If one thread opens a file with read privileges, other threads in the same process can also read from that file. The key benefits of threads derive from the performance implications. So, it takes far less time to create a new thread in an existing process than to create a brand new process. It takes less time to terminate a thread than a process. It takes less time to switch between two threads within the same process than to switch between processes. Threads enhance efficiency in communication between different executing programs. Actually, in most operating systems, communication between independent processes requires the intervention of the kernel to provide protection and the mechanism needed for communications. However, because threads within the same process shares memories and files, they can communicate with each other without invoking the kernel. Thus, if there is an application or functions that should be implemented as a set of related units of execution, it is far more efficient to do so as a collection of threads rather than a collection of separate processes. Let's say, for example, of an application that could make use of thread is a file server. So, as each new file request comes in, a new thread can be spawned for the file management program. Because a server will handle many requests, many threads will be created and destroyed in a short period. So if the server runs on a multi-processor computer, then multiple threads within the same process can be executing simultaneously on different processors. Further, because processes or threads in a file server must share file data and therefore coordinate their actions, it is faster to use threads in shared memories than processes and message passing for these coordinations. So, the thread construct is also useful on a single processor to simplify the structure of a program that is logically doing several different functions. So, Here is the example of the uses of threads in single-user multiprocessing system. No? So we have the foreground and background work. So for example, in a spreadsheet program, one thread could display menus and read user input, while another thread execute user commands and updates the spreadsheet. This arrangement often increases the perceived speed of the application by allowing the program to prompt for the next command before the previous command is complete. Number 2, of course, is the asynchronous processing. Asynchronous elements in the program can be implemented as threads. Let's say, for example, as a protection against power failure, one can design a word processor to write its random access memory. That is RAM buffer to this once every minute. So a thread can be created whose sole job is periodic backup and that is schedule itself directly with the OS. There is no need for fancy code in the main program to provide for time checks or to coordinate input and output. The number 3 is the speed of execution. A multi-threaded process can compute one batch of data while reading the next batch from a device. On a multiprocessor system, multiple threads from the same process may be able to execute simultaneously. Thus, even though one thread may be blocked for an input-output operation to read in a batch of data, another thread may be executing. Number 4 is the modular program structure. Programs that involves a variety of activities or a variety of sources and destinations of input and output may be easier to design and implement using threads. In an operating system that supports threads, scheduling and dispatching is done on a thread basis. No? Hence, most of the state information dealing with execution is maintained in thread-level data structures. And there are, however, several actions that affect all of the threads in a process and that the OS must manage at the process level. So, for example, suspension involves swapping the address space of one process out of main memory to make room for the address space of another process. Because all threads in a process share the same address space, all threads are suspended at the same time. Similarly, termination of a process terminates all threads within that process. The thread functionality, like processes, threads have execute stage and may synchronize with one another. So we look at these two aspects of thread functionality in turn. So the thread states, as with processes, the key states for a thread are running, ready, and blocked. Generally, it does not make sense to associate suspend state when threads because such state are process level concepts. In particular, if a process is swapped out, all of its threads are necessarily swapped out because they are all share that address space of the process. And that's what we have here. There are 4 basic thread operation associated with a change and a thread state. So number 1 is a spawn, no? This is typically when a new process is spawned, no? A thread for that process is also spawned. So subsequently, a thread within a process may spawn another thread within the same process, providing an instruction pointer and arguments for the new thread. The new thread is provided with its own register context and stack space and placed on the ready key. So block, when a thread needs to wait for an event, it will block. no, saving its user register, program counter, and stack pointers. No, the processor may now turn to the execution of another ready thread in the same or a different process. Unblock. So when the event of which a thread is blocked occurs and thread is moved to the ready queue. Then finish. When a thread completes its register, context and stack are deallocated. So as a significant issue is whether the blocking of the thread result in the blocking of the entire process. So in other words, if one thread in a process is blocked, does this prevent the running of any other thread in the same process, even if that other thread is in the ready state? Clearly, some of the flexibility and power of threads is lost if the one block thread blocks an entire process. Now, we return to this issue subsequently in our discussion of user level versus kernel level threads. But for now, let us consider the performance benefits of threads that do not block an entire process. So based on this figure, it shows a program that performs two remote procedures, no calls. Now the two procedure calls. The two different hosts to obtain a combined result. So in a single threaded program, the results are obtained in sequence. So the program has to wait for a response from its server in turn. Rewriting the program to use a separate thread for each RPC results in a substantial speed up. We need to take note that if this program operates on a uniprocessor, the request must be generated sequentially and the results processed in sequence. However, the program waits concurrently for two replies. On a uniprocessor, multiprogramming enables the interleaving of multiple threads within multiple processes. So in this figure, no, 3 threads in 2 processes are interleaved on the processor. Execution passes from one thread to another, either when the currently running thread is blocked or when its time slice is exhausted. Okay, so we have what we call thread synchronization. So all of the threads of a process share the same address space and other resources, such as open files. And the alteration of a resource by one thread affects the environment of the other threads in the same process. It is therefore necessary to synchronize the activities of the various threads so that they do not interfere with each other or corrupt data structure. So, for example, if 2 threads each try to add an element to a doubly linked list at the same time, one element may be lost or the list may end up malformed. No? The issue raised and the techniques used in the synchronization of threads are in general the same as for the synchronization of the process. So we have the type of threads. So we have the user level and kernel level threads. So there are 2 broad categories of thread implementation as what we have here. So the latter are, of course, we have the user level and the kernel level threads. The latter are also referred to in the literature as kernel supported threads or lightweight process. The user level, in a pure ULT facility, all of the work of the thread management is done by the application. In the kernel is not aware of the existing of the figures. So any application okay. So As what I mentioned, any application can be programmed to be multi-threaded by using a thread libraries, which is package of routines for ULT, or when we say ULT, user level threads. The threads library contains code for creating and destroying threads, for passing messages and data between threads, for scheduling thread execution, and for saving and restoring thread context. So by default, an application begins with a single thread and begins running in that thread. No? This application and its thread are allocated to a single process managed by the kernel. At any time that the application is running, the application may spawn a new thread to run within the same process. Spawning is done by invoking the spawn utility in the threads library. Control is passed to that utility by a procedure call, and the thread library creates a data structure for the new thread and then passes control to one of the threads within the process that is the ready state using some scheduling algorithm. So when control is passed to the library by the context of the current thread is saved, and when control is passed from the library to a thread and the context of that thread is restored. So the context essentially consists of the contents of user registers, the program counters, and the stack pointers. All of the activity described in the preceding paragraph takes place in user space and within a single process. The kernel is unaware of this activity because the kernel continues to schedule the process as a unit and assign a single execution state for ready, running, block, and others to that process. Now, as what we have here, this will be an example that should clarify the relationship between thread scheduling and process scheduling. Suppose that process B, no, this one, at the right, no, second, is executing in its thread 2, the state of the process and 2 ULTs are that are part of the process are shown in figure. No, each of the following is a possible occurrence. So the application executing in thread 2 makes a system call that blocks B. Then a clock interrupt passes control to the kernel, and the kernel determines that the current running process B has exhausted in its time slice. Then the thread 2 has reached a point where it needs some action performed by thread 1 of process B. Then thread 2 enters block state, and thread 1 transitions from ready to running, and the process itself remains in the running state. The corresponding state diagram, of course, must display in letter D. Okay, so while this multi-programming can result in a significant speed up of the application, there are applications that would benefit from the ability to execute portions of the code simultaneously. So the kernel level threads. In the pure kernel level threads facility, all of the work of thread management is done by the kernel. So there is no thread management code in the application level, simply an application program interface or the API to the kernel thread facility. Windows is an example of this approach. So, on the face of it, while there is a significant speed up by the using kernel level threads, multi-threading compared to single-threaded processes, there is an additional significant speed up by the using ULTs. However, whether or not the additional speed up is realized depends on the nature of the applications involved. If most of the thread switches in the application required kernel mode access, then a ULT-based scheme may not perform much better than a KLT-based scheme. So, another one is the combined approaches. No? Some operating system provide a combined ULT and KLT facility. No? So in a combined system, thread creation is done completely in a user space as it bulk of the scheduling and synchronization of threads within an application. The multiple ULTs from a single applications are mapped onto some number of KLTs. The programmer may adjust the number of KLTs for a particular applications and processor to achieve the best overall results. In a combined approach, multiple threads within the same application can run in a parallel on multiple processors. And a blocking system called need not block the entire process. If properly designed, this approach should combine the advantages of the pure ULT and KLT approaches while minimizing the disadvantages. Solaris is a good example of an operating system using this combined approach. And the current Solaris version limits the ULT and KLT relationship to be 1-to-1. Other arrangement, as we have said earlier, the concept of resource allocation and dispatching unit have traditionally been embodied in the single concept of the process, that is as 1:1 relationship between threads and processes. There has been much interest in providing for multiple threads within a single process, which is a many-to-one relationship. However, as this figure 2, as you can see here, now we have 1:1, many-to-one, one-to-many, and many-to-many. It shows that the other two combinations have also been investigated as what I've mentioned. No? The many-to-many relationship is the idea of having a many-to-many relationship between threads and processes has been explored in the experimental operating systems. So, as what we have here, there are the concept of domain and thread, and a domain is a static entity consisting of an address, space, and ports through which messages may be sent and received. The thread is a single execution path with an execution stack, processor state, and scheduling information. As with the multi-threading approaches discussed, multiple threads may execute in a single domain, providing the efficiency gains. And however, it is also possible for a single user activity or application to be performed in multiple domains. A thread exists that can move from one domain to another. So the use of a single thread in a multiple domain seems primarily motivated by a desire to provide structuring tools for the programmer. So let's say, for example, consider a program that makes use of an input-output subprogram. In multiple programming environment that allows users bound process, the main program could generate a new process to handle I/O and then continue to execute. However, if the future progress of the main program depends on an outcome of an I/O preparation, then the main program will have to wait for the other I/O program to finish. The multi-core and multi-threading. The use of multi-core system to support a single application with multiple threads, such as might occur on a workstation. And we are all familiar with that, right? A video game console or a personal computer running a processor instance, intense application raises issues of performance and application design. I think we first look at some of the performance implication of a multi-threaded application and a multi-core system, and then describe a specific example of an application design to exploit multi-core capabilities. So the potential performance benefits of multi-core organizations depend on the ability to effectively exploit the parallel resources available to the application. So as what we have here, we have a formula here on getting the focus first on a single application running to a multi-core system. That is Amdahl's law. Excuse. So the distribution of work to multiprocessor and cache coherence overhead. So this result in a curve where performance peaks and then begins to degrade because of the increased burden of the overhead of using multiple processors. So, however, software engineers have been addressing this problem, and there are numerous applications in which it is possible to effectively exploit a multi-core system. It reports on a set of database applications in which great attention was paid to reducing the serial fractions with the hardware architectures. So, these figures shows the result. No? As this example shows, database management system and database applications are one area in which multi-core system can be used effectively. Many kinds of servers can also effectively use the parallel multi-core organizations because servers typically handle numerous relatively independent transactions in a parallel. So in addition to generally purpose server software, a number of classes of applications benefit directly from the ability to scale throughput with the number of cores. So here is the list of a general purpose server software. So we have the multi-threaded native applications. The multi-threaded applications are characterized by having a small number of highly threaded processes. Examples of threaded applications include Lotus Domino or Siebel CRM or the Customer Relationship Manager. Another is the multi-process application. So multi-process applications are characterized by the presence of many single-threaded processes. So example of course is the multi-process application include the Oracle database, SAP, and the PeopleSoft. For Java applications embrace threading in a fundamental way. So not only does the Java language greatly facilitate multi-threaded applications, but the Java virtual machine is a multi-threaded process that provides scheduling and memory management for Java application. The Java application that can benefit directly from multi-core resources include application servers such as Sun Java Application Server, Bayes WebLogic, IBM WebSphere, and the open source Tomcat Application Server. And all applications that use a Java 2 Platform Enterprise Edition or the G2EE platform. The application, all applications that use Java 2 Platform Enterprise Edition, application server can immediately benefit from multi-core technology. And I think each and every one of you are very much familiar with different Java platform. The multi-instance applications. No? Even if an individual application does not scale to take advantage of a large number of threads, it is still possible to gain from multi-core architecture by running multiple instances of the application in parallel. So if multiple application instances require some degree of isolation, virtualization technology, specifically for hardware, of course, of the operating system, can be used to provide each of them with its own separate and secure environment. So as you can see here, in the discussion of the thread, no, multi-thread, multi-core, and so on, we discussed, no, and we tackled, or we encompassing with the discussions of data structure, the object-oriented programming, the database application, specifically the one-to-one, many-to-one, one-to-many, and many-to-many relationship. And that is within the database applications. So actually, this will be an example, no, of a Valve game software. I don't know if you're familiar with the Valve game software. Valve is an entertainment and technology company that has developed a number of popular games, no, as well as the Source engine, one of the most widely played game engines available. Source is an animation engine used by Valve for its games and licensed for other game developers. So in recent years, Valve has reprogrammed the Source engine software to use multi-threading to exploit the power of multi-core processor chips from Intel and AMD. So the revised Source engine code provides more powerful support for Valve games such as Half-Life 2. So Valve's perspective threading granularity options are defined as, of course, the coarse threading. No? The coarse threading, individual modules called system are assigned to individual processor. In the Source engine case, this would mean putting rendering on one processor, the artificial intelligence on another, and physics on another, and so on. And this is straightforward. No? In essence, each major module is single-threaded, and principal coordination involves synchronizing all the threads with a timeline thread. Again, in developing a game, no, it is important for us to be good in physics, in artificial intelligence at the same time, of course. Now, another one is the fine-grained threading. So many similar or identical tasks are spread across multiple processors. So let's say, for example, a loop that it iterates over an array of data can be split up into a number of smaller parallel loops in individual threads that can be scheduled in parallel. So specifically when it comes to the array, no, array of data. Hybrid threading, this involves the selective use of fine-grained threading for some systems and single threading for other systems. Valve found that through coarse threading, it could achieve up to twice the performance across two processors compared to executing on the single processor. For those who are gamer here, I think it is very familiar with you. But this performance gain could only be achieved with contrived cases. For real-world gameplay, the improvement was on the order of the factor of 1.2. Valve also found that effective use of fine-grained threading was difficult. The time per work unit can be variable, and managing the timeline of outcomes and consequences involve complex programming. The Valve found that a hybrid threading approach was the most promising and would scale the best. So as multi-core system with 8 or 16 processors became available, Valve identified systems that operate very effectively being permanently assigned to a single processor. An example is sound mixing, no? For those who are sounds lover, no, which has little user interaction, is not constrained by the frame configurations of Windows and works on each set of data. Other modules such as scene rendering can be organized into a number of threads so that the module can execute on a single processor, but achieve a greater performance as it is spread out over more and more processor. So as I mentioned, this will be the rendering, no? So this figure actually illustrates the thread structure for the rendering module. No, for those who are a game developer, they are all familiar with the rendering, no, mixing, and so on. In this hierarchical structure, this will be an example of a hierarchical structure, no? Higher level threads found lower level threads as needed. So the rendering module relies on a critical part of the source engine, the word list, which is the database representation of the visual elements in the game's world. So the first task is to determine what are the areas of the world that need to be rendered. And the next task is to determine what objects are in the scene as viewed from the multiple angles. Now, then comes the processor-intensive work. The rendering module has to work out the rendering of each object from multiple points of view, such as the player's view, the view of the TV monitors, and the point of view of reflections in water. So some of the key elements of the threading strategy for the rendering module, of course, is the construct scene rendering list of multiple scenes in parallel. Overlap graphic simulation is also considered. Compute character bone transformation for all characters in all scenes in parallel, and allow multiple threads to draw in parallel. So this will be the Windows 7 thread in SMP process. So Windows process design is driven by the need to provide support for a variety of OS environment. No? So process supported by different OS environments differ in number of ways. So according the native process, structure, and services provided by the Windows kernel are relatively simple and general purpose, allowing each OS subsystem to emulate a particular process structure and functionality. So in this figure, based on one in RAS 11, it illustrates the way in which a process relates to the resources it's controlled for users. It controls or uses. Each process is assigned a security access token called a primary token of the process. So when a user first logs on, Windows creates an access token that includes the security ID for the user. So every process that is created by or runs on behalf of this user has a copy of this access token. The Windows uses the token to validate the user's ability to access secured objects or to perform restricted functions on the systems and on secured objects. The access token controls whether the process can change its own attributes, and in this case, the process does not have a handle open to its access token. If the process attempts to open such a handle, the security system determines whether this is permitted, and therefore whether the process may change its own attributes. Also related to the process is a series of blocks that define the virtual address space, as what we have here, which is currently assigned to this process. So the process cannot directly modify this structure, but must rely on the virtual memory manager. So, which provides a memory allocation service for the process. And finally, the process includes an object table which with handles to other objects known to each process. And this figure shows a single thread. In addition, the process has access to a file object and to section object that defines a section of shared. We have here the process and thread objects. So the object-oriented structure of Windows facilitates the development of general-purpose process facility. Windows makes use of two types of process-related objects, the processes and the threads. No? A process is the entity corresponding to a user job or application that owns resources such as memory and often files. A thread is a dispatchable unit of work that executes sequentially and is interruptible so that the process can turn to another thread. So in letter A, figure 4.111, no? 4.11 rather A. So each Windows process is represented by an object whose general structure is shown here in this figure. No? So each process is defined by a number of attributes and encapsulates a number of actions or services that it may perform. So a process will perform a service when called upon through a set of published interface methods. So when Windows create a new process, it uses the object class or type defined for the Windows process as a template to generate a new object instance. So at a time of creation, attribute values are assigned, and a Windows process must contain at least one thread to execute. That threads may then create other threads. So in multi-processor system, multiple threads from the same process may be executed in parallel one. So in this figure, no, figure 4.11b, thread object, it depicts the object structure for the thread object. No, but we need to take note that some of the attributes of thread resemble those of a process. So in those cases, the thread attribute value is derived from the process attribute value. So for example, the thread processor affinity is the set of processor in a multiprocessor system that may execute this thread. And this is a set is equal to or subset of the processor affinity. We need to take note that one of the attributes of a thread object is context, which contains the values of the processor registers when the thread last ran. So the information enables thread to be suspended and resumed. Furthermore, it is possible to alter the behavior of the thread by altering its context while it is suspended. So this will be the sample of the Windows process object attributes. So this one is the Windows thread object attributes. So the next will be the multithreading. Windows support concurrency among processes because threads in different processes may execute concurrently. So it means to say that it will appear to run at the same time. So moreover, multiple threads within the same process may be allocated to separate processors and execute simultaneously. So actually run at the same time as I mentioned. So a multi-threaded process achieves concurrency without the overhead of using multiple resources. So threads within the same process can exchange information through their common address, space, and have access to the shared resources of the process. Threads in different processes can exchange information through shared memory that has been set up between the two processes. An object-oriented multi-threaded process is an efficient means of implementing a server application. So for example, one server process can service a number of clients concurrently. So the thread states, an existing Windows thread is one of the 6 states. So we have the ready, no? A ready thread may be scheduled for execution. The kernel dispatcher keeps track of all ready threads and schedule them in priority order. A standby threads has been selected to run next on a particular processor. The thread waits in this state until the processor is made available. If the standby thread's priority is high enough, the running thread on that processor may be preempted in favor of the standby thread. Otherwise, the standby thread waits until the running thread blocks or exhaust of its time slice. So as what we have here now, we have the ready, we have the transition waiting, running, terminated. And the standby at the same time, no? But of course, no, as what I mentioned earlier, based on what we have here, so the running state, no, once the kernel dispatch, once the kernel dispatch performs a thread switch, the standby threads enter the running state and begins execution and continuous execution until it is preempted by the higher priority thread, exhausts its time slice, blocks or terminates. In the first two cases, it goes back to the ready state as what we have here. So preempted, proceed to the ready state again. For the waiting, all the threads enters the waiting state when one is blocked on the event of 2, it is voluntarily waits for a synchronization purposes. An environment subsystem direct the thread to suspend itself. So when the waiting condition is satisfied, the thread moves to ready state if all of its resources are available. For the transition, a thread enters the state after waiting if it is ready to run but the resources are not available. So for example, the thread stack may be paged out of memory. So when the resources are available, the thread goes to the ready state. And the terminated. A thread can be terminated by itself, by another thread, or when its parent process terminates. So once housekeeping cores are completed, the thread is removed from the system, or it may be retained by the executive for future reinitializations. The support of OS subsystem. The general purpose process and thread facility must support the particular process and thread structures of the various OS environment. It is the responsibility of each OS subsystem to exploit the Windows process and thread features to emulate the process and thread facilities of its corresponding OS. In this area of process thread management is complicated and we give only a brief overview here. So the process creation begins with a request for a new process from an application. So the application issues a create process request to the corresponding protected subsystem, which pass the request to the executive. The executive creates a process object and returns a handle for all object to the subsystem. So when Windows creates a process, it does not automatically create a thread. In that case of Win32, a new process must always be created with an initial thread. Therefore, for the Win32 subsystem calls, the Windows Process Manager again to create a thread for the new process, receiving thread handle back from Windows. So the symmetric multiprocessing support. Windows support SMP hardware configuration. So the thread of process, including those of an executive, can run on any processor. So in the absence of affinity restriction explained in the next discussion, the kernel dispatcher assign a ready thread to the next available processor. This assures that no processor is idle or is executing a lower priority thread when a higher priority thread is ready. So this assure that no processor, as I mentioned, is idle. No? So as a default, the kernel dispatcher uses the policy of a soft affinity in assigning threads to processor. So the dispatcher tries to assign a ready thread to the same processor it last ran on. So this helps reuse the data still in that processor memory caches from the previous execution of the thread. It is possible for an application to restrict its thread execution only to a certain processor, and that is the hard affinity. This time, Solaris thread and SMP management. So multi-threaded architecture for Solaris makes use for separate threaded related. They have the process. This is the normal Unix process can and include the user's address space stack and process control block. They have also the user level threads implement through a threads library in the address space of the process, and these are invisible to the operating system. Lightweight process, it can be viewed as a mapping between ULTs and kernel threads. So then the kernel threads, these are the fundamental entities that can be scheduled and dispatched to run on one of the system processor. So in this figure, no, it illustrates the relationship among these four entities. We need to take note that there is always exactly one kernel thread for each LWP. So an LWP is visible within a process to the application. Thus, LWP data structure exists within their respective process address space. At the same time, each LWP is bound to a single dispatchable kernel thread, and the data structure for that kernel threads is maintained within the kernel address space. So a process may consist of a single ULT bound to a single LWP. So in this case, there is a single thread to execution corresponding to the traditional Unix process. When concurrency is not required within a single process, an application uses this process structure. If an application requires concurrency, its process contains multiple threads, each bound to a single LWP, which in turn are each bound to a single kernel thread. So in addition, there are kernel threads that are not associated with LWPs, and the kernel creates, runs, and destroys these kernel threads to execute a specific system functions. So the use of kernel threads rather than kernel processes to implement system functions reduces the overhead of switching within the kernel. Of course, from a process switch to the thread switch. So, of course, the motivation, the three-level thread structure in the Solaris is intended to facilitate thread management by the OS and to provide a clean interface to applications. So in addition, an application has access to hardware through an application programming interface consisting of system calls. The API allows the user to invoke kernel services to perform privileged tasks on behalf of the calling process, such as read or write a file, issue a control command to a device, create a new process or thread, or allocate memories for process to use, and so on. For the process structured, so the general term for the process structure of the traditional Unix system with that of Solaris. So in typical Unix implementation, the process structure includes the process ID, the user ID, a signal dispatch table, which the kernel uses to decide what to do when sending a signal to a process. The file descriptors, which describe the state of the files in use by this process, a memory map, which defines the address space of this process, and a processor state structure, which include the kernel stack for this process. Solaris retains this basic structure but replace the processor state block with a list of structure containing one data block for the WP. So the thread execution, this is simplified view of both thread execution states. So these states reflect the execution status of both a kernel thread and the WP bound to it. So as mentioned, some kernel threads are not associated with an LWP. The same execution diagrams apply. So this will be the states, no? Run, on proc, sleep, stop, zombie, and free. This one. So with the run, as what we have here, no? The thread is runnable. That is, the thread is ready to execute. So on proc, the thread is executing on a processor. Sa sleep, the thread is blocked. For the stop, no, the thread is stopped. For the zombie, the thread resource, the thread has terminated, and for free, the thread resources have been released, and the thread is awaiting removal from the OS thread data structure. So a thread moves from on proc to run if it is preempted by a higher priority thread or because of time slicing. A thread moves from on proc to sleep if it is blocked and must wait an event to the return the run state. Blocking occurs if the thread invokes a system call and must wait for the system service to be performed. And a thread enters the stop state if it is a process is stopped. And this might be done for debugging purposes. So interrupt as threads. No? Most operating system contains two fundamental forms of concurrent activity. So process and interrupts. Process or threads cooperate with each other and manage the use of shared data, is structured by means of a variety of primitives that enforce mutual exclusion and that synchronize their execution. Interrupts are synchronized by preventing their handling for a period of time. Solaris unifies these two concepts into a single model, namely the kernel threads and the mechanism for scheduling and executing kernel threads. To do this, interrupts are converted to kernel threads. So the motivation for converting interrupts to thread is to reduce overhead. The interrupt handlers often manipulate data shared by the rest of the kernel. Therefore, while a kernel routine that accesses such data is executing, interrupt must be blocked. So even though mass interrupts will be affect that data, typically the way this is done is for the routine to set the interrupt priority level higher to a block interrupts and then lower the priority level after access is completed. And these operations take time. No, the problem is magnified on the multiprocessor system because the kernel must protect more objects and may need to block interrupts on all processors. And the solution in Solaris can be summarized listed here. So when an interrupt occurs, it is delivered to a particular processor and the thread that was executing on that processor is pinned. So a pinned thread cannot move to another processor and its context is preserved. So it is simply suspended until the interrupt is processed. The processor then begins executing an interrupt thread and there is a pool of deactivated interrupt threads available so that a new thread creation is not required. The interrupt thread can execute to handle the interrupt. If the handler routine needs access to a data structure that is currently locked on some fashion for use of another executing thread, the interrupt threads must wait for access of the data structure. An interrupt thread can only be preempted by another interrupt thread of higher priority. So experience with Solaris interrupt threads indicates that this approach provides superior performance to the traditional interrupt handling strategy. For Linux, so Linux process and thread management, a processor task is Linux is represented by a task underscore struct data structure. So the task, this is command data structure contains information in a number of categories. So we have state, scheduling information, identifiers, interprocess, links, time in timers, file system, address, and so on and so forth. So as you can see here, same with the Linux process and thread models. This will be the Linux clone plugs, no? So when the Linux kernel performs a switch from one process to another, it checks whether the address of the page directory of the current process is the same as that of the to be scheduled process. If they are, then they are sharing the same address space, so that a context switch is basically just a jump from one location to another location code. Although clone processes that are part of a same process group can share the same memory space, they cannot share the same user stack. No? Thus the clone could create separate stack spaces for each process. The Mac OS, no? So the Mac OS provides a pool of available threads. Designer can designate portion of applications, called blocks, and that can be dispatched independently and run concurrently. The OS will provide as much concurrency as possible based on the number of cores available and the thread capacity of the system. Although other OS have implemented threads pools, Grand Central Dispatch for Mac OS provides a qualitative improvement in case of use and efficiency. So a block, as what we have here, is a simple extension of C or other languages such as C++. So blocks are scheduled and dispatched by means of queues. No? The application make use of system queues, no, provided by the GCD, and may also set up private queues or keys. No? Block are put onto as key as they are encountered during program execution. The GDC or the GCD rather then uses those keys to describe concurrency, serialization, and callbacks. So queues or keys are lightweight user space data structure, while generally makes them far more efficient than manually managing threads in locks. So for example, here is the HGF, not the keys GF. So in addition to scheduling block directly, the application can associate a single block and key with an event source such as timer, network socket, or file descriptor. Every time the source issues an event, the block is scheduled if it is not already running. This allows rapid response without an expense of pulling or parking a thread on the event source. So the first line of the function body analyze the document. So the second line updates the application internal state, and the third line tells the application that the statistics view needs to be updated to reflect this new state. And this code, which follows a common pattern executed in the main thread, the design is acceptable so long as the analysis does not take too long, because after the user clicks the button, the main thread of the application needs to handle that user input as fast as possible so it can get back to the main event loop to process the next user action. But if the user opens a very large or complex document, the analyze step may take an acceptably long amount of time. A developer may be reluctant to alter the code to meet this unlikely event, which may involve application goal of global objects. Thread management, callbacks, argument marshalling, context objects, new variables, and so on. But with GCD, a modest addition to the code produce the desired results. So we need to take note that all functions in GCD begins with dispatch underscore. No, the outer dispatch underscore async call puts a task on a global concurrent queue or key. That this tells the OS that the block can be assigned to the separate concurrent key of the main key and executed in parallel. Therefore, the main thread execution is not delayed. So when the analyze function is complete, the inner dispatch async call is encountered. This directs the OS to put the following block of code at the end of the main key or queue to be executed when it reaches the head of the key or queue. So with very little work on the part of programmer, the desired requirement is met. So in summary, some operating system distinguish the concept of process and thread. So the former related to resource ownership and the latter related to program execution. This approach may lead to improved efficiency and coding convenience. In a multi-threaded system, multiple concurrent threads may be defined within a single process. And this may be done using either user-level threads or kernel-level threads. User-level threads are unknown as to the OS and are created and managed by a threads library that runs in the user space of a process. User-level threads are very efficient because a mode switch is not required to switch from one thread to another. However, only a single user-level thread within a single can execute at a time, and if one thread blocks, the entire process is blocked. Kernel-level threads are threads within a process that are maintained by the kernel. Because they are recognized by the kernel, multiple threads within the same process can execute in parallel on a multiprocessor, and the blocking of thread does not block the entire process. However, a mode switch is required to switch from one thread to another. That's it, and thank you.